Okay, so thank you, Peter. So today I'm so grateful that OPS gives me the opportunity to present our latest work on CAPI and OpenCAPI accelerated Postgres. So I'm Peng Fei from IBM China System Lab. Okay, so let's give some very brief introduction to what is Postgres. So Postgres, according to their own website, it's one of the world's most advanced open source relational database. So from the database popularity ranking, we can see that Postgres is ranked as number 4th. So from number 1 to number 3, it's 3 enterprise databases. So this means Postgres should be very popular in various areas, including maybe cloud, enterprise, and research. So that's why we choose Postgres as our target. Okay, so let's give some very high-level view of what we have done. So currently, we are able to accelerate Postgres with regular expression matching, and for users, for the end users, we have 2 interfaces for them to use our acceleration. The first one is a user-defined function, which is a UDF. We created a new function in this name, and if the users want to use our acceleration, they need to call this function in their SQL language script. So, which means most of the users would not be very happy with this because it requires them to change their scripts, change their codes. So that's why we have another way which is implemented as Postgres hooks and plugins, and this enables the user to use the standard SQL language in this form with where clause and a regular expression matching operator. Then the users are okay to use our acceleration. So this is exactly what we are trying to present to the end users to use our acceleration. Okay, so let me give some very high level, introduction about the overall architecture for both software and hardware. So from this screen, we can see that on the left side is the host memory. There are various data structures inside the host memory. And for those orange boxes, they are the Postgres internal data structures for pages. In Postgres, every relation or every table is comprised of a large amount of pages. And those pages will be loaded from storage to the buffer cache on the host memory. And then we have multiple threads which will be working in parallel to process those pages. And then for each thread, they are going to process a part of those pages, and then they will find the columns that will be matched with the regular expression, and find the columns and copy that into another memory buffer in user space. We call it packet buffer. And for every thread, they have a packet buffer, and for every packet buffer, they will finally be touched by the regular expression engine on the FPGA via CAPI and OpenCAPI by virtual address pointers. So that is the advantage of CAPI and OpenCAPI. So those regular expression engines, they are connected with an AXI interconnect, and they will talk with the host memory by a bridge, which is the AXI to CAPI or OpenCAPI bridge. For CAPI, it's AXI to PSL. For OpenCAPI, it's AXI to OpenCAPI TRX. So by using this AXI interconnect and this bridge, the regular expression engine, they are able to fetch the packets. That is the strings that will be matched with the regular expression. And they will fetch the contents of this buffer to the hardware. And then they will perform the regular expression matching. And when they finish their job, they will write back the result also with the by using the AXI interconnect, write back that into the buffer. We call it a result buffer. And then the software is going to use this result buffer and present it to the Postgres upper level software to the end user so that the end user can finally see the result of the regular expression matching result. And then on the hardware, this structure allows not only the regular expression engines, they allow other type of engines like general query engine or any other types such as hash join or aggregation. But those engines are still under construction in progress. And we also have a plan to have a hardware job manager on the FPGA so that the job scheduling will have less overhead. But this component is also in progress. Currently, all the engines, they are controlled by software directly with MMIO access. Okay, so this is the overall architecture. And then let's take a look at some of the details of our regular expression engine. So this engine is written by our team from scratch in HDL, in RTL. It is comprised of multiple pipelines. Each pipeline is able to process one string and one time. And inside that pipeline, we also have multiple processing units, which allows the engine to match one string with multiple regular expression patterns at the same time. So which means they have two dimensions of parallelization. And then the whole architecture is configurable for both hardware and software. So for hardware, during the image building phase, we are able to define the number of pipelines. We are able to define the number of processing units. And during runtime, the regular expression pattern is also configurable by using hardware and runtime. Okay, so those 2 pages, I introduced some of the details of the hardware. Then let's take a look at what we have done for the software. So for the software, we are basically building our whole software on top of Postgres hook and plugin flow. So for Postgres hook and plugin flow, it is basically the customer path, customer scan, and customer execution methods. There are 4 very important hooks to implement our acceleration. Those 4 hooks are begin scan, execute scan, end scan, and explain scan. So in begin scan, this is where the most of the interaction between software and the hardware happens. We will prepare the internal data structures for the whole scan work, and then we will extract the regular expression pattern from a SQL language given by user, and then we'll start the multithreading worker to enable the software talk with hardware to get the result of hardware and to process every details. And then after the whole work finished by the hardware, we will go to the execute scan. In execute scan hook, the results will be harvested. So the results will be processed by the software, and the tuples, which means the rows in the tables, in the relations, they will be reconstructed. And then this result will be returned to the PostgreSQL internal data structures so that the end user will see the result of their regular expression matching. And then the third hook is the end scan hook. In this hook, we will do most of the cleanup jobs, which means every temporary buffers allocated during the whole scan will be freed at this stage. And we also have another explain scan. So in this explain scan, we will define how the users will look when they call the explain statement in the PostgreSQL client console. So this is the basic high-level structure of how we implement our software. So here I'm talking about when we make the software and the hardware communicate with each other, I'm talking about the multi-threading worker. So what is that? So this is a very low-level software that enables the software talking with hardware in a very parallel way. We define the worker, define the thread, and define the jobs. So for each Postgres scan, we will have one worker that allows the software to communicate with the hardware. And in each worker, we have multiple threads. And for every thread will be working in parallel. And in every thread, we will have multiple jobs. So for each job, they will be executed in sequentially. So which means, threads, they are parallel, but within the threads, the jobs will be executed in sequential. The reason is that, because for every thread, what they are going to process is fixed. The amount of data bytes that will be processed is fixed. So, which means if you have a very large table, then for every thread, you may need to allocate a very large packet buffer, which will have, tremendous overhead of when you deallocate this memory buffer. So to reduce the size of this buffer, we need to define multiple jobs. Those jobs will reuse this packet buffer so that the size of the packet buffer will be smaller. So I will give some more details in the later stage when I explain the performance. I will show you how the number of jobs will impact the overall performance, especially for the cleanup phase. Okay. So this is what I have. This is for the overview of the details of hardware and software. So let me show you a short video to see so that you can feel that what we have done, what you can do with our acceleration. Okay, this is the video that is recorded by my screen. I'm sorry. Hold on. Let me show you the. Where is my pointer? Here we go. Okay, this is a record of my screen in the PostgreSQL console. This is the table I used to perform the test. It has the schema. They have two columns, one for packet, the other for ID, and then we will load the hook, the library that enables CAPI, and we will set the parameters and for enable CAPI mode to define the number of threads we're going to use, to define the number of jobs we are going to use. And then after all of the parameters be set, we're going to call the standard SQL language with regular expression operator, and this result, 128 rows are matched with this operation. And then we will call explain analyze to show the real customer scan path that we use for this operation, and the execution time will also be shown with this one. To to compare the difference between CPU and the CAPI, here we will disable the CAPI mode to run in pure CPU mode. So they are using the same SQL language, and the result is exactly the same. And when you run the explain analyze, you will see that they are using CPU parallel worker, and the runtime is much slower. So I will give some more details on the performance evaluation. Okay. Okay, let's get back to the charts. So I just show the video of how our acceleration will be looking like in the real server. So let's give some more details about the performance evaluation. So to measure the performance, we have our environment set up. So we use the Power9 server, 2 sockets. Every socket have 22 cores, and we have 512 gigabytes in memory. And for the FPGA card, we use a Xilinx VU9P FPGA card. And for the CAPI, all of our work are based on CAPI2 and Snap2. We are using Snap2 as our development framework. This also allows us to move to OpenCAPI with minimal effort, because we have a OpenCAPI version Snap, which is called OpenCAPI acceleration framework. Lu Yong will present details for that framework later. And then for the engines, we use eight engines. Each engine has 16 packet pipelines, which means each engine is able to process 16 strings at the same time. And the FPGA logic is running at a clock frequency of 225 megahertz. And for Postgres, we have different parameter set. We are running with Postgres version 11.2. And then for the shared buffers, we use two sets, 4 gigabytes and 1 gigabyte, to see the difference, to see if they have any impact to the performance. And there are also other parameters set for Postgres. And for the queries, we use the standard SQL language I just said in the previous slides. And for the tables to be tested, we have some synthetic tables, and for each table we have 2 columns, one for string and the other for ID. And then for table size, we have different number of tables with different number of rows for different data points. Okay, here is the result of compare our acceleration with CPU version. We have 4 data points, 2 for CAPI, the other 2 for CPU, with buffer cache 1 gigabytes and 4 gigabytes respectively. So from this picture, we can see that compared with CPU, our acceleration, our CAPI acceleration is going to have 5 times to 10 times speed up compared with the CPU. So when the table is larger, the speed up drops from 10 times to 5 times. That is because when the table is larger, then the CPU version, they are going to use the CPU parallel workers. So that speed up the CPU version, but we still have 5 times advantage. And when the table is very small, we also have some drop for the speed up. That is because the table is too small, so the overhead of the engine configuration will have some cost, will have impact to the overall performance. Okay, this is the overall performance comparison with CPU and our acceleration. And then we also have some measurement to see how the number of threads impact the overall performance. This picture shows that when the number of threads changed from 1 to 8, the overall query time drops significantly. So it's very good to see that if we have more threads, that means more works will be parallel, especially when we process the packet buffer. And then we also have some detailed breakdown for each query. We break the whole query time to 4 parts. The first part is the packet preparation. This means that for the software, when we copy, the software will process the Postgres internal data structures, process the pages, then copy the columns from the internal data structure to the packet buffer. This time is measured as packet preparation in green. And then in the blue, for the blue part, it's the hardware run, which means the regular expression engine be configured and to read the packets and to process the whole packets, to perform the regular expression matching and to write back the result. That is the hardware run. And then for the yellow part, it's the clean up. And for the orange part, it's all the other times consumed by, for example, to read the shared buffer, or something others. And then in this measurement, we can see that as the number of threads increase, the time consumed on the packet preparation and the hardware run decreased very significantly. So that's why the overall query time reduced very significantly when the number of threads increased. So for each data point, I didn't say the number of jobs. For each data point, we use the optimal number of jobs for each data point. Then why we use, why I say I use the optimal number of jobs? That is because, in the next chart you will see that if we have the fixed number of threads, which is 8 threads, if we change the number of jobs from 1 to 10, we will see that the breakdown, especially for the cleanup time, which is the deallocation of shared memory buffer, this will drop very significantly. So this means that because the overall runtime, overall query time for a fixed number of threads is almost the same, especially for hardware run and for packet preparation. So if you cost too much time on the cleanup, you will have performance dropping. So the philosophy behind this is that we need to have more jobs so that the shared buffer used by each job is very small. We only need to allocate a very small amount of shared buffer so that when we deallocate this buffer, the cost will be reduced. Okay, so this is why that's why we choose to use multiple jobs and to allow the jobs to share one very small shared buffer. Okay, so let's go to the next page. So actually, we also have some other work items in progress. For example, we are working on a solution on not use the packet buffer, but we are working on a solution to allow the regular expression engine or allow any engine on the FPGA to access the Postgres internal pages directly with the page pointers in virtual address. So this will save the amount of time when you copy the internal data structure to the packet buffer. This is what we can benefit from CAPI and OpenCAPI, but this is still in progress. Okay, and then the other work item is the job manager, where it's in progress. It will reduce the cost of job configuration. So if you configure the job, you need to have a large amount of MMIO accesses. So those will have impact to the overall performance if you have too many jobs. So, but if we have a hardware job manager, that will have a benefit for reducing the configuration overhead, because the hardware job manager, they will configure the engines directly without MMIO access. And we also have other types of work items, including developing other types of engines, such as the general query engines or hash join engines, but all of those engines are still in progress. Okay, this is a summary of what we are going to present maybe in the next few months, including the more performance and analysis, hardware job manager, and use the page pointers directly, other types of engines, and adoption to OpenCAPI. I believe adoption to OpenCAPI, move from CAPI 2 to OpenCAPI should be very easy if all of our work are based on Snap or OpenCAPI acceleration framework. And we are also seeking opportunities working with the clients or partners for other types of database, because currently we only have the solution for Postgres. There should be other requirements for maybe MariaDB or any other MongoDB or any other type of database if the customers or partners they are interested in. And then here we go to the conclusion. So our demo shows that Postgres and CAPI, they can work well, especially for the regular expression matching. And it is a very valuable demo or showcase that needs to be paid more attention if we want to have a more sophisticated solutions or products in the future. And also we are, because we are a demo team, we are a showcase team. Most of our engineers are from hardware domain. We are chip engineers, so we are not very familiar with the for the applications, for the softwares. So we learned that from scratch by Googling. But if there's experts from database areas, they can join us to look at the details. I believe we are able to present more powerful, more production level solutions in the future. So that's all I want to present. Any questions? Thank you.
Thank you for your talk. I just have a quick question about the runtime breakdown. So you were talking about the configuration of the regular expression engines using MLIO. And I was wondering in your runtime breakdown, which of the four categories that you had included this configuration of the engines?
Okay, the question is that, in the performance breakdown, which part stands for the configuration overheads? Okay, so actually this breakdown, with all of the configuration overheads are included in the blue part. Yeah, so this blue part includes both configuration and the runtime for hardware. So I didn't, print too much details because, I'm not sure if this is the best situation to present so many technical details. Yeah, but maybe I think at the end of this year we will have a paper, technical paper to be ready. Then if you want, I can send you a copy of that. There will be more detailed analysis on the performance breakdown.
I have a question.
So, okay.
Can you give me an idea of how much throughput there is here?
Yeah. Peter's question is that currently this chart shows a latency performance. We don't have a throughput performance. The reason is that to measure the throughput, we need to have multiple clients access the server database at the same time. So right now our hardware engine, it's still, we still need some extra work to make those engines to handle requests from different process, from different queries at the same time. But this will be ready very soon, maybe in September. But right now, the number is not very stable. We are still working on that to present the throughput number.
Other questions?